Process Safety, Module 1, Screening Experiments by Denis Pratt, Sanofi. This training on process safety is divided into 3 modules. This one is a basic training dealing with early experiments in the lab, especially in the university. The goal is to build a safety awareness for students in chemistry. You should be able to understand the GHS symbols and hazard statements given in the safety datasheets, avoid accidents by a safe handling of unstable material and mixtures, and analyze a DSC graph. One cannot design a green process if it is not safe. This is clearly integrated in the 12 principles. This does not mean that all hazardous materials and processes are banned, but at least that enough experiment and risk analysis should be made to ensure a safe scale-up. In other words, if the hazard cannot be avoided, at least the risk should be very low. Despite all the wellness that chemistry provides, most of people have a negative image of chemistry, having in mind the catastrophic events such as Bhopal in India or Toulouse in France. These accidents have reinforced process safety culture, and as a result, they are relatively rare. We have acquired enough knowledge to identify the most hazardous situations, and stringent regulations, such as the so-called Seveso regulation, impose very complete hazard and risk analysis when hazardous processes are run on a large scale. It is important to note that the catastrophic accidents are seldom the result of an uncontrolled reaction in a vessel. In Bhopal, water was accidentally introduced into a storage tank containing methyl isocyanate. In AZF plant in Toulouse, a storage of ammonium nitrate exploded for a still unclear reason. Other explosions occurred during distillation of flammable liquids or even after the ignition of a glucose dust cloud in air. Actually, even if they are not catastrophic, most chemical accidents happen in labs, especially in the university. Most often, they only affect the chemist who carries out the hazardous experiment, but they can be severe and even result in fatalities. There are several reasons for this. Firstly, the safety culture is not developed in research. Secondly, students are enthusiastic but inexperienced. They are sometimes not aware of all hazards of a reagent and the risk of an operation. I will not tell you what I did when I was young. The desire to save time is the most frequent cause of accidents. Moreover, the return of experience is very limited. I encourage you to look at the safety alerts in organic process research and development, and before using a reagent, to check in the Balzeris handbook if there are incompatibilities with the solvents or other reagents. In order to give a definition of process safety, we have to define both terms. First of all, safety is the absence of risk. But what is a risk? What is the difference between hazard and risk? Hazard is an intrinsic property. A material can be flammable, corrosive, etc. The hazard associated with a lion is that it is a powerful predator. The risk appears when you are exposed to the hazard. As long as the lion is in the cage and you are at a safety distance from the cage, you're safe. The cage and the safety distance act as safety barriers. In the lab, the main barrier against exposure by inhalation is the fume hood. Gloves protect you against cutaneous contact. The definition of a process is a series of operations needed to obtain and isolate a product. Bear in mind that the chemical reaction may not be the most hazardous operation. If each of them generates specific risks which must be managed. The purpose of a hazard and risk analysis is to identify the hazards of each operation and decide the safety barrier needed to eliminate the hazard or reduce the risk. The first step of the hazard and risk analysis is to identify the hazards linked to the materials used in the process. These hazards are given in the safety datasheets in a worldwide global harmonized system. This system uses pictograms which give an idea of the hazard nature. We'll take the example of ammonia. The warning word is high, danger, and there are four types of hazards: compressed gas, corrosive, toxic, and toxic to environment. The GHS statements are more precise and are divided into three categories: physical hazards with H200 statement. Here, H280 contains gas under pressure and H221 flammable gas. Health hazards with H300 statements. Here, H314 causes severe skin burns and eye damage. H331 toxic if inhalated. And environment hazard H400 statements, such as this one, very toxic to aquatic life. They are completed with precautionary statement P something, which gives storage and handling advice, such as P284, where respiratory protection. The physical hazards are divided into subcategories. The intrinsic properties for unstable materials, for example, H201 means explosive, mass explosion hazard. The flammability, reaction with air in the presence of a flame. The hazard level is linked to the flash point and the boiling point. The reaction with fuel for oxidizing agents. The reaction with water. The reaction with metals, that is to say, the corrosion. This is an important point, as many accidents are the result of an undesired reaction between incompatible materials. In the storage area, one must be careful not to store oxidizing reagents with solvents. In a reactor, if the vessel material is not compatible with the reagent. In the container for waste solvents, frequent accidents happen when unreacted oxidizing agents or acyl chlorides arrive in the container. Of course, the risk analysis must be adapted to the hazard level and the scale. For the preliminary experiments on few milligrams, the awareness of the hazards, the common sense, and the usual protection, fuel hood, safety goggles, gloves, are enough. For a scale-up on a couple of grams, a basic risk analysis is needed. In the KiloLab, it is important to formalize the risk analysis, which must include an incompatibility matrix and an assessment of the stability of materials and reaction mixtures. In the pilot plant, calorimetric experiments must be conducted, and in production, all possible deviations must be analyzed and safety safeguards established. Do not forget that a safe reaction in the lab can be catastrophic in a plant. In the lab, the cooling capacity is very high, and a strong exotherm can be undetected. This is because the reaction heat varies in proportion to the volume of the reaction mass, whereas the cooling rate varies only in proportion to the surface of the vessel wall. Besides, glass-lined reactors in the plant have a low heat transfer coefficient. To limit the risk in the lab, one has to design safe processes. Take some time to write equilibrated equations and to identify the actual stoichiometry and the byproducts. For example, the hydrogenation of a nitro group necessitates 3 mol half hydrogen, not 2, and gives 2 moles of water. This explosion in the lab was the result of an excess of chlorine in a mixture containing ammonium chloride. Nitrogen chloride was formed, which is highly unstable. Also, sodium azide gives hydrazoic acid in the presence of weak acids, and this product is volatile and explosive. Sodium cyanide gives a highly toxic hydrogen cyanide in the presence of very weak acids. The process is not limited to the noble reaction. One has to design adapted treatment for safe workups. The risk analysis in the lab must identify the possible incompatible mixtures, such as acid with some metals, oxidizing and reducing agents, and don't forget that a formyl group has a reductive potential. In a safe process, the reagent is dosed at the temperature at which the reaction takes place. There is no accumulation. Unfortunately, it is common to see in the literature unreproducible procedures such as the hydride solution was introduced at minus 78 degrees and the mixture was allowed to warm up, or all reagents were charged and the mixture was heated up to reflux. At which temperature the reaction actually starts? A process cannot be robust if it is not safe. Select the safest order of addition, limiting reagent into the reaction mixture, strong acid into water, excess hydride into water. Do not leave a reaction unattended until it is stabilized. The temperature must be steady, no visible exotherm, no gas evolution. And avoid leaving reactions run overnight under reflux. The probability to have a black residue is high. If possible, limit the temperature jacket to 10 degrees under the reflux temperature. Sometimes we cannot avoid hazardous materials. We need to detect them immediately, but by chance the most unstable groups are well known. Nitro, nitrites, peroxide, hydrazines, everything with two heteroatoms linked, but also alcenes. Such products may violently decompose in the oven, nitro compounds, or even in the rotavap, azides. Never totally evaporate azide solutions. Never distillate peroxidable ethers. Do not dry nitro compounds above 40 degrees. If you are equipped, check the stability by differential scanning calorimetry. DSC is a powerful and inexpensive method, which requires only a couple of milligrams of material. It permits to determine the melting point, the temperature of decomposition of materials or reaction mixtures, their energy of decomposition, and any incompatibility with the equipment material. The sample is introduced in a small crucible which is closed. It is introduced in the cell which also contains an identical empty crucible which serves as reference. The oven is submitted to a regular temperature gradient, usually 3 to 5 Kelvin per minute, from 0 degrees to 300 or 400 degrees. The cell contains sensors, which measure the heat flow exchange through the bottom of the crucibles, and the thermogram will plot the heat flow difference between the crucible containing the sample and the reference crucibles, hence the term of differential scanning calorimetry. This is a classical thermogram. On the x-axis, the temperature or the time, because the gradient is constant. On the y-axis, the heat flow in watt per gram. The exotherm phenomena are above the baseline. In this example, an endotherm is measured first, starting at 150 degrees, and corresponds to the fusion of the material. A very strong exotherm is detected starting at circa 250 degrees. It corresponds to the decomposition of the sample. The area under the peaks gives the energy in joule per gram. In this case, a nitroaromatic compound, it is 1000 joule per gram, which means an explosive character. An energy of 100 joule per gram corresponds roughly to a temperature increase of 50 degrees. This is the limit of a hazardous phenomenon. Above 500 joule per gram, the decomposition cannot be controlled. It is very hazardous. As I said previously, DSC can be used to detect incompatibilities with the equipment material. Gold crucibles are used to mimic inert glass-lined reactors. Stainless steel or Hastelloy crucible can also be used. In this case, the material decomposes at 140 degrees in the gold crucible with a high energy 1200 joule per gram and with a very high maximum heat flow 37 watt per gram. In the stainless steel crucible, the decomposition starts at a lower temperature 115 degrees and the decomposition is as energetic but less violent. DSC are usually run under air, but they can also be carried out under an oxygen atmosphere to detect oxidation phenomena or nitrogen. In conclusion, organic chemistry, like any activity, generates risks. There is no more reason to be afraid of it than to fear to take your car or cross the street. One needs to be aware of the hazards of the process, starting with those linked to materials, then to reactions, but also other operations. Check also the incompatibilities by a rapid bibliography. Then, carry out a risk analysis adapted to the scale. What are the hazards of each operation? Can I eliminate the hazard, for example by dosing a reagent solution rather than a solid reagent? Can I reduce the risk, for instance drying at a reduced temperature? If not, what safety barrier can I put in place? Then, protect yourself and your colleagues. Make your experiments in closed fume hoods. Wear the protective equipment, lab coat, safety goggles, gloves. Be careful and note all your observations. They will be very useful for the scale-up, exotherm, induction periods, or gas evolution. You are now ready to carry out safely screening experiments in the lab. If you wish to know more and how to conduct risk analysis for scale-up, connect to Module 2. If you are interested in reaction calorimetry, connect to Module 3. Thank you for your attention.